Today we are reviewing Chapter 9 about circles. I warned you pretty much every day throughout this chapter that this test can be a killer because there are so many definitions and theorems. So I warned you pretty much every day to study as we go. So hopefully you took me up on that. If not, I hope that you will at least believe me that you need to study tonight before your test tomorrow. So the first thing it says is you need to know your definitions to be able to locate these things inside of a circle, not to write out definitions. You will not need to write out any of your definitions or theorems. You will not have any matching or fill in the blanks. But if I ask you to find something in a circle, you need to be able to find that particular thing. And we will do some examples of that. Then be able to use the theorems that we have had to solve for angles or arcs or segment lengths in a circle. Again, you will not need to write out any of these theorems, but you have to know what they say to be able to solve a problem that has these things occur in it. So listed out here are the main theorems and corollaries. If a line is tangent, that line is perpendicular to the radius. In the same circle, congruent arcs would have congruent chords. So if two chords are marked as the same, that would mean two arcs are the same as well. A diameter that's perpendicular to the chord bisects it. Measure of an inscribed angle is equal to half the measure of the arc. If a skipped one, an angle that's in a semicircle is a right angle. If a quadrilateral is inscribed, opposite angles are supplementary. Measure of an angle formed by a chord and a tangent is half of the arc. An angle formed by two chords inside the circle is half the sum of the arcs. An angle formed outside the circle, whether it's by secants or tangents, is equal to half the difference of the arcs. Then the three from the last lesson, when two chords intersect inside, we can take the product of those broken pieces. And if we're working with a secant segment, we do the full length of the secant segment times the external part. And if we're working with a tangent, we square that length. Big key, practice. Practice, practice. It is one thing to be able to do a particular night of homework when those problems are covering only the three theorems that were in that lesson. It is a completely different thing to be able to solve a question on the test where it doesn't give you any frame of reference for which lesson we learned it in or any hint as to which theorems to use and apply. So they will be in mixed order and won't tell you which theorem you'll need to apply. So you need to know these theorems to be able to apply them to particular problems. So in light of that, let's look at some practice problems. So the next page in your packet is this handout. The first type of question here is how vocabulary will be tested. You'll be given a diagram and asked to name certain things in that picture. So name a chord that is not a diameter. Where is a chord in that circle that is not the diameter? DC or CD, order of letters does not matter. Symbols do matter, though. What kind of a thing is a chord? A segment. So we need our segment symbol above that. Okay, order of the letters doesn't matter, so DC or CD, either way, but symbols do matter. A chord is a segment because it has endpoints that are on the circle. A diameter, where's a diameter in that picture? AD, again, order doesn't matter, so DA is fine, but what kind of a thing is a diameter? A segment. A radius. OD or AO or OA. And there's actually one more. OC is not specifically drawn on there, but if we drew it, it would in fact be a radius. So we could also call that a radius. And what kind of thing is a radius? A segment. You only need to name one. Yeah, but any of those would be correct answers. A tangent. Where's a tangent in that picture? AB. And what kind of a thing is a tangent? A line. So we need the line symbol above it. Definition of tangent is a line that shares only one point in common with the circle. And a secant. Where is a secant? DB. And what kind of thing is a secant? A line. Okay, definition of secant is a line that contains a chord. So even though in our picture it has endpoints, by definition a secant is a line. So we need to have the appropriate symbols there. Okay. There were more definitions than just these. So look over the definitions from the listed sections and make sure that you know how to locate some other things in a circle, like inscribed angles or central angles or points of tangency and things like that. Questions on vocabulary? Okay, so then to solve some problems. Angle AOB is not drawn in the picture, but we can draw it in there. So if I draw angle AOB, by definition, what kind of a thing is angle AOB? What kind of an angle is it? It is a central angle because its vertex is at the center. It is a central angle because the vertex is O and O is the center of that circle. What is the measure of a central angle? How does a central angle compare to the arc? It's equal to the arc. So AOB is 120. Okay, a central angle is the same size as the arc that it cuts off. So AOB would be 120, since the arc from A to B is 120. ADB. So it is already drawn in, but I'll just highlight it out. ADB is what kind of an angle? Inscribed angle, because its vertex is on the circle. And how does the measure of an inscribed angle compare to the arc? Half of the arc. So ADB would be 60. ACB is an angle created outside of the circle. What is our rule for an angle outside of the circle? Half the difference of the two arcs. So when it is created outside of the circle, we need to half the difference of the two arcs. So the arc from A to B, the quick way, is 120. What about from A to B, the long way?
It would be
240. How do you figure? Subtract from 360. So if there's 120 between A and B on one side, there must be 240 between A and B on the other side, because a whole circle is 360. Then our rule for an angle outside of the circle is that that angle is half of the difference of the two arcs. So it is half of 240 minus 120, which would be 60. Questions on that? EAD. In our picture, if we trace out angle EAD, it is made by a chord and a tangent. What is our rule for an angle made by a chord and a tangent? It is half of the arc that is cut off. A tangent and a radius are perpendicular. So EAO would be 90. A tangent and a radius are perpendicular. So EAO would be 90. But EAD, a chord and a tangent, is half of the arc that's cut off. So how big is that arc from A around to D? It's 240 from A to B. From A to D would be 200 because this bottom part here we were given as 40. So our angle then would be 100, half of that arc. An angle made by a tangent and a chord is half of the arc that's cut off. If it happens to be a tangent and a radius, that would be a right angle or 90 degrees. Questions on any of those? Okay, for the next group of questions, we move down to the next picture. We're given angle AEB is 20. And we're asked for AFB. They would be the same. Why are they the same? What kind of angles are they? Inscribed. And what's our rule about an inscribed angle? If they share the same arc, they will be the same. But what's our rule about the size of an inscribed angle? Half the arc. So how big is the arc? 40. And so then any angle that bounces it back into that is going to still be 20. Okay, so they are both 20.
Wait, but how do you know that's 20?
Our rule for an inscribed angle is that an inscribed angle is half of the arc. So since AEB is 20, then that arc would have to be 40. All right. In the next part, new information, not building off the last information. So this time arc AB is 95 and arc EF is 25. And we want to know how big AGB is, the angle outside. What is our rule for an angle outside of the circle? Half of the difference. So half of 95 minus 25 is 35. An angle formed outside, whether it's by secants or tangents, will be half of the difference of the arcs inside of that angle. Questions on that one? For number 12, this time, AB is 70, EF is 30, and we are asked to find AHB. It would be half of 70 if H were the center.
But isn't it half of 70?
Half of 70 plus 30. An angle formed inside that is not at the center is half the sum. And actually, I'm sorry, I said something wrong. If it were the center, what's our rule for a central angle? It would be equal to. So that'd be a problem with this being the central angle then, because how could it be equal to 30 and 70? So then our rule is that it is the average of them, or half of the sum of the two arcs. So that means that angle will be what? 50. 30 and 70, 100, half of that is 50. If it is a central angle, if the vertex is at the center, it is equal to the arc. But if the vertex is somewhere else inside of the circle but not at the center, then it's half the sum of the two arcs, or the average of the two arcs. Questions on that? Okay, for the last one in this group, this time AB is 85. We're given EHF is 59. The other side of that would be the same thing because they're vertical angles. It's easier to fit it on the other side. And EF is what we're looking for, so I'll call that X. Our rule is the same as the last question because we have the same stuff here. We're still working with an inside angle, but this time we're looking for an arc, so we need to set up an equation. So just like the equation that's in number 12, we're going to fill in what we know. angle is equal to half of one arc plus the other arc. So the same type of question as the previous one, since it's still the angle inside, but this time it's an arc that we're missing instead of the angle that we're missing. How do I solve that equation? What do I do first? Multiply the whole thing by 2, which gives me what? $118 is x plus 85, and then subtract 85, which gives me 33. Questions on any of them in that group? Okay, for number 14, looking at segment pieces here, what equation would I set up to solve for x in number 14? Five times x equals 6 times 3. Our chords is that we can multiply the broken pieces. So 5x is equal to 18, and divide by 5. It's not pretty, so we'll just leave it. Or you could divide it out. It's 3.6. That would be a fine answer as well. Biggest mistake that students make on this, I can tell you the most common wrong answer that I will be given is that x is 4. Okay, that's wrong. X is 3.6. But that is the most common mistake that students make, is to make the assumption that both of those chords have to have the same length. So since CD is 9, they would say AB needs to be 9, so that means x is the leftovers, which would be 4. That is not true. All chords do not need to be the same length. In a circle, there are some long chords and some short chords. So they do not add up to the same thing, but their products will be the same thing. So multiply the broken pieces. Do not add and subtract the broken pieces. Questions on that? Number 15, working with secants. What is our rule for a secant? X plus 2 times 2, whole thing, times the outside. So for the top one, the whole length would be adding those two pieces, and then times the outside. For a secant, full length times outside. Equals, what about for the bottom one then? 5 plus 3 times 3, or 8 times 3, whole length times outside. What do I do first to solve that equation? Distribute. So it gives me 2x plus 4 equals 24. And then 8 times 3 is 24. Subtract the 4. So 2x is 20 and x is 10. Obviously not drawn to scale. Questions on that one? Number 16. 9 plus 4 times 4. 4. Whole length. We do 13 times 4 and try to take a square root. It is not a pretty number. So instead of giving an ugly decimal, we'll just take a square root here. Square root of 13 is not a pretty number, but what about the square root of 4? It's 2. So we get 2 square roots of 13 would be the best answer there. A decimal would be acceptable, but the best answer is the exact answer of 2 square roots of 13.
What did you multiply 13 times 4?
If I multiply 13 times 4 and take a square root, it's just not pretty. It would be correct. I would accept the decimal, but it's not going to be an exact answer where 2 squared root of 13 is an exact correct answer. We like exact and precision in math. Number 17, we are told that CA and CB are tangents to the circle. What do we know about the lengths of tangents? What do we know about CA? It's 12 as well. All tangents to a circle from a point will be the same length. So now, I have a triangle here. I know I have a 5, I know I have an X, and I know I have a 12. What kind of a triangle is that? It is a right triangle. How do I know it's a right triangle? Because I have a radius and a tangent, and a radius and a tangent are perpendicular. That is what one of our first theorems said, is that a radius and a tangent will be perpendicular to each other. So now I have a right triangle in which I know 2 values and want to know another value. How do I solve that? Pythagorean theorem. 5 squared plus 12 squared equals x squared. There were a few of our theorems that did not come up in any of these questions, so just a few other reminders of what those theorems said. In a circle, if chords are congruent, arcs will be congruent. We're not going to do that proof, but just borrowing that picture. If chords are congruent, arcs will be congruent, was one of our theorems. So if we know we have 2 congruent chords and we know how long one of the arcs is, the other arc must be the same. Another theorem that we didn't use at all is that if I have a diameter and a chord that is perpendicular, what happens to that chord? It's cut in half. It's bisected. Those 2 pieces are the same size then, the top and the bottom. So that was one of our theorems that didn't come up in here. A special case of a theorem that didn't come up is if I have the diameter drawn in, that creates what? 2 equal halves, or what do we call those halves? Semicircles. And if I inscribe an angle in that semicircle, what do I know about that angle? It's a right angle. An angle inscribed in a semicircle is a right angle. And one more that didn't come up is if I have a circle and a quadrilateral inside of it, what do I know about opposite angles? They are supplementary, or they add up to 180. Okay. A lot of theorems, a lot of rules for different types of pictures, and you have to know what to apply when. You will not need to state or write out any of them, but you have to know what to apply when in these questions. So study, practice. In your book, beginning on page 369, there's a chapter review, and then after that a chapter test. That would be a really good place to go for practice problems. Okay? So beginning on page 369 and then going on through page 371 or 372 are a lot of practice problems for the types of problems that you will see on the test.